Let me start with the classical theorem from GAGA, which is sort of a dead example for us. It says that if X is a compact complex variety, then it admits exactly one algebraic structure. Well, actually, at most one algebraic structure. What does it actually mean? That you can rephrase it as follows. If X is a complex analytic variety, compact, and Y is another complex analytic variety, and you have an isomorphism, a biholomorphism between them, then this biholomorphism is algebraic. So, okay, let's start with saying that X is projective and Y is also projective. And if you have a biholomorphism between these two varieties, then this biholomorphism has to be algebraic. Sorry. Great. That's what happens in the compact world. But the non-compact world is much wilder. And counterexamples to a GAGA for non-compact varieties have been known for a very long time. And the first of them was by Serre. So I'll write counterexample in quotes, because, well, they don't contradict this statement. So the first one is due to Serre, and the construction is as follows. You take C without 0 times C cross, and I claim that this variety has infinitely, namely uncountably many algebraic structures. And why is it so? Let's rewrite this manifold as C2 quotient by Z2, by lattice, C2. Yeah, that's because C cross is isomorphic to C mod Z as a complex analytic variety. And now I'm gonna choose an element omega, whose imaginary part is greater than 0, and I'm gonna map everything to C mod Z plus omega Z, which is of course an elliptic curve, which I'll denote by E omega. And the map is as follows. It sends xy to x plus y omega. What can we say about this map? First, it's definitely surjective. Second, it's actually an affine bundle. That is to say, it's a torsion over a vector bundle. In this case, a trivial bundle. So I'm going to write it here. Torsion over O E omega. Second, since it's an affine bundle over an algebraic variety, it has to admit an algebraic structures. And an algebraic structure making this map algebraic. Let's call this map F omega. Let me comment a little bit on the first part. So, why is it an affine bundle? Let's see what the fiber of a zero is. It's just a set of numbers x and y, whose sum is with these coefficient zeros. So the fiber is x plus omega w equal to 0. And each fiber is a torsor of this vector space. Because if you add x and y whose sum with this coefficient to 0, then they will map to the same point. Great. And also, I forgot to say here that this affine bundle is non-trivial. That means that it doesn't have a section. And of course it doesn't, because this is a chain variety. It can't have any compact subvarieties. Great. So by choosing omega in any way you want, you can construct an algebraic structure here. And these all will be different algebraic structures. Okay. We prove that C star cross C star has uncountably many algebraic structures. Great. Let me talk now about two more examples which were known before. My work with Rodion came up. So the second example is due to a Polish mathematician Jelonek. This one starts with an affine curve. Let's call it C. And let's also assume that its genus is high enough. I believe that 1 is enough, but okay. Maybe 1 is enough. Okay, what is the Picard group of this curve? How to compute it? Well, we can realize C is an open subspace in a compact curve, C bar. And therefore, the Picard group of C bar can be restricted to the Picard group of C, and there will be some kernel which is finitely generated. Okay. In particular, the Picard group of C has infinitely many elements, even uncountably many. Okay, and now let's take any line bundle, L, and look at its total space. And let's compare it to C cross C. Well, they're not isomorphic unless L is a trivial line model. I'm not going to prove it, but you can check it yourself if you want. I'm not actually sure if it's always true in genus 1, but okay. Greater than 1. In this case, it's definitely always true. Okay, great. Now let's look at C as just a complex manifold and try to understand what its Picard group is. In the complex world, we have an exponential exact sequence. C, O, X, O, X dot. Well, not X, C. Even Cn. Let's write the associated sequence of cohomology. We have H1 of OCn, then we have the Picard, the analytic Picard group of C, and then we have H2 of Cn. This is 0. It's a Stein variety. It's 0. Great. The analytic Picard group is 0. In particular, this isomorphism actually holds in the analytic category. So, therefore, the variety C cross VC, like complex numbers, has uncountably many complex numbers. Sorry, not complex, algebraic. Great. This is only 2 examples of surfaces with uncountably many algebraic structures I know. And in the next few examples, we are gonna talk about surfaces with countably many algebraic structures. And so the example that Rodion and I invented also has countably many algebraic structures. In all the examples I'm gonna present to you, we are gonna start with a surface, compact surface, and then remove a curve from it. And then we'll prove that the remaining surface has countably many algebraic structures. And for some reason, I don't know, in all these examples, this curve is going to be an elliptic curve. I don't know of any examples where we remove a curve of genus 2 or any other genus. So first, let's take, it looks awful. I'm going to try again.
I thought it was pretty good.
Maybe. Okay, third example. Let's take an elliptic surface X over a curve. First, I'm going to introduce the Shafarevich state group of the surface, and then we're going to see how these are going to help us construct algebraic structures on such an elliptic surface. So, definition. The group SHA of X over C, this is a Cyrillic letter SHA. It's called Shafarevich state group. It's defined as a first cohomology of the following sheaf. I'm going to denote it as ought not of X over C. What does it mean? It means that we consider the sheaf of automorphisms of X which preserve fibers. Automorphisms that preserve fibers. But an abelian variety can have many automorphisms. For example, it has an automorphism -1. We're not interested in them. We're interested in all automorphisms that lie in the connected component of unity for all fibers of the elliptic surfaces. Of the elliptic surface. Connected component of unity of ought of X B for all fibers. This looks pretty abstract, but actually this group has a pretty clear algebraic meaning. And to see that, let's take an element of this cohomology group and represent it as a checker cycle. That means that first we cover C by some open subsets in the analytic topology. Everything in the analytic topology, by the way. For any two intersections, we consider an automorphism phi ij. So it's an automorphism of over u ij. So let's say xij over uij. And we know that these automorphisms satisfy co-cycle conditions. Okay, and I denote xij let's call this map pi. So xij is just the preimage of uij. And now I'm gonna obtain another elliptic surface which locally looks like the one we started with. I'm gonna take xij and glue them in a different way. I have an automorphism for, xi. I have an automorphism for any two pair of indices. So I'm gonna glue xi, which contains xj, through this automorphism to xj. And in this way, I'm gonna get another elliptic surface. So let me call it x phi. It's also an elliptic surface over C, and it's isomorphic to x over each of ui. And the geometric meaning of the Serre group is that it parameterizes all these elliptic surfaces which look like x locally in an elliptic topology over C. So it parameterizes elliptic surfaces that look like x locally over the base. Great. For quite a lot of elliptic surfaces, the Serre group is non-trivial. For example, if x is a k-free surface, then the Serre group looks like this. It's C mod some finitely generated subgroup, not necessarily a lattice. So the group can look pretty nasty. It can be non-Hausdorff. Well, but it's not trivial. That's the point. Second example. If C is an affine curve, then the Serre state group is trivial. How can we exploit these two facts? We can start with an elliptic surface over a compact curve, and then we can remove a few fibers. So we're going to get an elliptic surface over a non-compact curve, and its Serre state group is going to be trivial. Great, but if we do the same thing with all these other elliptic surfaces, I'm going to call them Serre state twists. Then we're going to get the same surface after removing fibers. Yeah, but Serre state twists of x. Okay, let me write something.
So then you're saying that analytically any such fibration has a section over an alpha curve.
No, it doesn't have a section. If it has a section, then it's, for example, a projective.
Over an affine.
It doesn't have to have a section, even analytically.
I see.
So the main idea here is that we, for example, start with an elliptic surface with a section, and when we deform this fibration a little bit so that this section disappears.
But doesn't your second example, if C is an affine curve, then this group is trivial?
Okay.
Doesn't that say exactly that?
Okay, over an affine curve it does have a section, yeah, you're right. But not over the compact curve.
Yeah. It was
okay.
Yeah.
Sorry for the confusion.
Are here some assumptions like no multiple fibers or something?
No multiple fibers. Okay, so XC is an elliptic surface without multiple fibers. And C is compact. And then we consider an open subset here. And we have another elliptic surface. Yeah, and we know that no matter which Chevrolet twist we take, we get the same surface here. But some Chevrolet twists are projective and some are not. How to know? It turns out to be pretty easy.
There are no singular fibers.
Without multiple fibers. There might be singular fibers.
Okay.
Okay, so let's assume that this elliptic surface also has a section. Then I claim that projective Chevrolet twists correspond to torsion in the Chevrolet group. Okay, so in this example, it's pretty easy to see that there will be, in the exemplification surface, I mean, that there will be countably many torsion points here, and in general, it's going to be the same. So if we restrict to see not all projective surfaces, we're going to get some surface which is the same analytically, but not algebraically. In particular, we proved that X naught has at least countably many algebraic structures.
So there's possibly uncountably many, but impossibly. Probably not.
No, there are still countably many algebraic structures. I'm not going to prove it.
Okay. So in fact, these are all of them, or there's more?
Actually, there are more of them, but there are still countably many.
Okay.
So I'm going to say not uncountably. Okay.
And so particularly, you actually can describe all of them in terms of.
Yeah. Okay, I'm not 100% sure that I can describe all of them, but I can at least describe more.
Right.
Because there are also log transforms, if you know what it is.
Okay.
So it is a way to make a fiber of an elliptic fibration multiple.
Ah.
Yeah, and this is also a source of other algebraic structures on X naught. So we just make the fiber which we remove to multiple, and we get something that potentially has another algebraic structure.
Cool.
Great. Okay.
C naught is just an open C?
C naught, yeah, it's an open, and it's obtained by removing a few fibers.
But no particular condition. Any will work.
Any will work. Well, we need to remove at least one.
The torsion, the order of the torsion is related to the minimal degree of a multisection.
Yeah, I think it is more or less equal. Great. So, any questions about this construction? Let's move on to the new example, which is from my paper with Rodion. And in this example, we also remove an elliptic curve, as already said. But there is no elliptic fibration. We take P2 and 9 general points in a very general position. Nine points in very general position. I put very general in quotes because it's a pretty weird notion of very generality. We'll see later. Great. Now we blow up these points. This surface contains an elliptic curve. That is the preimage of the unique elliptic curve that passes through these points. It has an elliptic curve E, and the square of this elliptic curve is 0. This is the curve that passes through U1. Let's remove it. And I claim that the remaining variety has countably many algebraic structures. X minus E has countably many algebraic structures. And moreover, they all come from the same construction. That is to say, we take P2, we take other 9 points on P2, we blow them up, we remove an elliptic curve, and we get a variety that is biholomorphic to this one, but not algebraically isomorphic. So I'm going to write it like this. For every algebraic structure on X minus E, there exists some 9 points Q1, Q9, and Q2, such that, so let's call XP here, such that XQ minus EQ is biholomorphic to XP minus EP. EP is the elliptic curve here, as you could guess. But no, this is biholomorphism is not of the rest.
Sorry for the stupid question, but the choice of 9 points, was it countable?
Yeah, there are countably many sets of 9 points, such that this is true.
Okay. Not all of them will work.
Not all of them.
Sorry.
Yeah, that's why this variety has countably many, not uncountably many.
Yes.
Yeah, great. And in the remaining half an hour, I'm gonna give you an idea of how one can prove such statement. The proof of the statement relies on the construction which I call Hopf transforms. And Hopf comes from a Hopf surface. So first, I'm going to start with some reminder on Hopf surfaces. What is a Hopf surface? It's obtained as follows. We take C2, we remove the origin, and then we quotient it out by some diagonal operator. Diagonal lambda mu, and let's assume that both lambda and mu, their absolute value is greater than 1. This surface is not algebraic, it's not even scalar. how one can see it, you can, for example, compute its Betty numbers and see that the first Betty number is odd. It's not however, there's a very simple way to make an algebraic surface out of a Hopf surface. That is to remove one of the two curves that sit inside it. What are these two curves? First, we have a curve which is obtained by quotienting the x-axis by lambda. Sorry, C star. And second, we have a curve which comes from quotienting the y-axis by me. They're both elliptic curves. I claim that if I remove this curve, for example, then the remaining surface is going to be a total space of a line bundle over this curve. Proposition. Let me do this annotation. So I'm going to call this Hopf surface H lambda mu. And I claim that if I remove from this Hopf surface this curve, E mu, then this surface is going to augment a vibration over E lambda, and it'll be a total space of line bundles. Let's prove it. It's not that hard. First, how to construct a map. It's just a projection to the first coordinate. I'm going to call this map F. So F of xy is x. Easy. Now, what's a fiber? Let's see. So let's take point x here, and the fiber is just going to be C. There's all points of the form xy. And we don't have to quotient by anything because, well, we don't want to change x. The fiber is C. And actually it's a torsor over C star, because we can multiply this second coordinate by any number. We also need to find the zero section. Where is the zero section? It's here. The zero section is lambda sitting inside H lambda mu. Okay, and that's pretty much it. We have the zero section, and we know how to multiply fibers by a number. Cool. Now let's vary mu and look on different Hopf surfaces. Then we are going to remove E mu and look at what remains. We already know that the total space of some line bundle remains. Therefore, we have a map from C star to the Picard group of E lambda, which is constructed as follows. We take mu and we map it to H lambda mu minus E mu. Great. What is this map? What can it be? Lambda is C star mod lambda. So as you can guess, this map is just quotient by lambda. Well, it requires some proof, but it's not particularly difficult to see. In particular, we notice from here that if we start with a line bundle of degree 0, then we can find countably many mu such that this is the total space of this line bundle. Because if we found one mu, then we can multiply it by lambda as many times as we want. Well, not as many times because we need this condition to be satisfied, but still, there are countably many of them. So we prove the following proposition, that for any line bundle on E lambda, there exist countably many mu such that the total space of L is isomorphic to H lambda mu minus E mu. Great. Any questions about it? Perfect. What we're going to do next is we're going to take the total space of some line bundle over E and remove the zero section. And I claim that there always exists a countable number of other elliptic curves, such that if we remove the same procedure with them and some line bundle over them, we get the same manifold. Analytically the same, of course. And the proof relies on Hopf surfaces. I'm going to make a sketch of a Hopf surface. So, well, let me draw it like this. And we have one elliptic curve here and a second elliptic curve here. This is E lambda. This is E mu. And we know that if we remove just one elliptic curve, then we are left with a total space of some line bundle over E lambda. So H minus E mu is the total space of L, let's call it L lambda. Now let's remove the second curve. H minus E mu minus E lambda. This corresponds to removing the zero section here. So it's going to be isomorphic to the total space of L lambda minus zero section. Of course, we can do it in the opposite order. We can first remove E lambda and then remove E mu. And therefore, we will get that this surface is also isomorphic to the total space of L mu minus zero section. Therefore, these two surfaces are isomorphic. However, this isomorphism is not exactly what we want because it swaps the neighborhood of the zero section and the neighborhood of infinity. But it's very easy to repair that. We just compose this isomorphism with some accent in Z to the inverse on each fiber. Okay, because so this is also isomorphic to the total space of L mu inverse minus zero section. And if we look at the isomorphism between this total space and this total space, then this isomorphism will preserve neighborhoods of zero sections. Cool, but that's not it. If we start with a line bundle, we can embed it in a Hopf surface countably many times, as we saw on that part of the blackboard. And therefore, we can find countably many of elliptic curves E mu, and pairs of E mu and a line bundle on them, such that we have this biholomorphism. We proved the following. Let's start with an elliptic curve, a line bundle is a big of P. And let's look at the surface taught L minus 0 section. I claim that there exist countably many pairs P prime, L prime, where E prime is also an elliptic curve, and L prime is in E0 P prime, such that these two surfaces are isomorphic, and the isomorphism preserves neighborhoods of zero sections. Any questions about it? Great. What happens here? We take some surface, taught L, then we remove an elliptic curve from it, and then instead re-glue some different elliptic curve. Great. We sort of want to do the same with already raised the theorem, but we want to do the same with an elliptic curve which sits in some blow-up of P2. However, we don't know if the neighborhood of this elliptic curve is isomorphic to total space of some line bundle. It's not always true, but it turns out that in some cases it is true. And that relies on a theorem by Arnold and Ueda. I never expected that sometime in my life I'm gonna use a theorem by Arnold, but it happened.
The fact that the Lagrangian fibration has a general fiber and abelian variety is by Arnold in the end. It's Arnold-Liouville theorem.
Okay, interesting.
You use it.
I think that even this result probably goes back to Grauer, who proved that the analytic neighborhood of a submanifold is unique if, like, higher cohomologies of the symmetric part of the normal bundle or something are zero. Some result like this.
Okay, so I'm gonna call the next part tubular neighborhood theorem.
But how do you know that this, so you exhibit some way to give some isomorphism between total space of a line bundle minus the section? There may be other way, no?
Out of what, sorry?
So you exhibit some isomorphism between total space of a line bundle of an elliptic curve minus its zero section. How can we rule out the possibility that there may be other isomorphism with maybe uncountably many line bundles? No, we saw some way to realize this isomorphism, but...
Yes, the proof relies on a general theorem proved by Uehara. He proved that all compactifications of the total space of a line bundle are obtained either by Hopf surface or by a projective bundle over E.
I see.
It's a pretty difficult theorem.
I see. Okay.
Okay. What is a tubular neighborhood theorem? In differential geometry, it says the following. Assume you have a submanifold, a real submanifold, in some compact, smooth manifold, real manifold, M. Then I claim that there is always a tubular neighborhood of N which is isomorphic to a tubular neighborhood of the zero section of the normal bundle. So there exists some neighborhood of N inside M such that U can be embedded into the total space of the normal bundle, N from N to M. Great. And of course, this theorem is not true in the complex analytic situation. It's only true for smooth manifolds. Well, why is it not true in the complex analytics world? The easiest example is to take any elliptic surface which is not isotrivial, and then look at any smooth fiber of this surface. What is its normal bundle? It's trivial. It's OD. But can a neighborhood of a fiber be isomorphic to E times some disk? No, because E times some disk doesn't contain any smooth varieties except for this elliptic curve. But any neighborhood of E here does contain a lot of different elliptic curves. Let me write it like this, that every neighborhood of X is not E times disk. Okay, but luckily there are many examples, then this theorem still holds for elliptic curves in surfaces. And that's what Arnold-Weber theorem tells us. Arnold-Weber theorem. It says the following. Let's consider an elliptic curve in a surface X. And let's assume that that's a normal bundle of E inside X is Diophantine. I'm going to define it later. Then the tubular neighborhood theorem holds in the analytic topology, in the complex analytic topology. The main problem here is with the word Diophantine. I'm going to define it in a moment, and the definition is defined. Very hard for me to understand how Arnold and Weber managed to come up with this definition.
In your setting, this follows from this result of Grauer, that from like way before this, which says that. So if the normal bundle is not torsion, then somehow, right, so Grauer showed that if you take the tangent bundle of your subvariety, tensored with the symmetric powers of the normal bundle, and H1 of that is 0 for all symmetric powers, then this tubular neighborhood theorem holds.
Wait. But here it's not enough for it to be non-torsion.
I see, yeah.
Yeah, so I guess that there are some additional conditions in Graber's theorem.
No. Just any complex submanifold satisfying the property that H1 of its tangent bundle tensored with the symmetric powers of the conormal bundle is 0 for all symmetric powers.
Wait, so is it true in complex analytic category or is it true formally?
Complex analytic.
Complex analytically. Okay, we'll discuss the terms at the top.
While in your case, you don't.
Huh?
What is the topology that you use here? The tubular neighborhood exists as there is
Euclidean topology.
Euclidean.
Yeah. Okay. How do we define Diophantine line bundles? Okay. So every line bundle gives us a point in the Picard group of E. Picard group, and we can identify the Picard group of E with the elliptic curve. Okay, and then we can consider the sequence L squared, L cubed, L to the fourth, and so on, and we are going to measure distances between 0 and these points. So we look at the sequence distance between 0 and Ln. Which method do we use? Well, basically any richest translation invariant. You don't even need it to be Riemannian. Okay. And the line bundle is called Diophantine if minus log of distance from 0 to Ln is O of log n. Not very illuminating, but actually it's sort of some generalization of a notion of a non-Liouville number. Some two-dimensional version. And what is a Liouville number? It's some number which is very well approximated by rational numbers. Yes, so this condition actually means that L is very badly approximated by torsion line bundles. Okay, and we know that the space of non-Diophantine line bundles has measure 0. Therefore, a very general, in the sense of measure theory, line bundle is Diophantine. The general line bundle on P is Diophantine. How much time do I have? Not many. So I'm going to try to wrap up. What does this theorem mean for us? That if we have an elliptic curve in the surface, and we are lucky enough so that it has a Diophantine normal bundle, then we can treat its neighborhood as a neighborhood in the total space of the normal bundle. So then, well, we can squeeze X a little bit, and we can assume that X is contained in the total space as a line bundle. And then we can perform the procedure with this total line bundle of removing the zero section and gluing another elliptic curve instead. Remove E and glue E prime instead. We can do it because we know how to do it with total space of line bundles. And now we can do it with any elliptic curve whose normal bundle is Diophantine. I call this surgery Hopf transforms. Why transforms and not transform? Because we can choose E prime in countably many ways. Any questions? In the remaining 5 minutes, I'm going to try to explain how to use Hopf transforms to prove the theorem about blow-ups of P2. So we're coming back to blow in up. Okay, we have X, which is the blow-up of P2 in some 9 points. And it contains an elliptic curve. If the points Pi are chosen in a very general way, very general in math-theoretic sense, then the normal bundle of E is Diophantine. That's an assumption that doesn't always happen. Then we can perform Hopf transforms with X. Countably many Hopf transforms. And we get some other surface Y, which contains some other elliptic curve F. I claim that Y is also a blow-up of P2. And to say it, we need to first compute the first Betti number of Y. That is pretty easy because we know that the first Betti number of X is 0. From this, we can conclude that the first Betti number of the complement is 0. And from this, we can conclude that the first Betti number of Y is 0. You need to just write a couple of non-exact sequences of cohomology. But there are many surfaces which are not non-rational, which still have a trivial Betti number. A Kaiser surface, for example. How to exclude this case? Here we're going to use that as a pair XE is a local Abasheva surface. It means that Kx is minus E. In other words, there exists some 2 form on X which has simple poles along P. 2 form omega with simple poles along P. And now let's look again at the Hopf surface. It is C2 minus 0. Watching by something. but again, well, diagonal operators. It also has a meromorphic two form, dx over x times dy over y. And if we remove the second curve, then this form has just one pole, and this pole is along an elliptic curve. If we remove the first curve, then it has a pole over the second curve. What I want to say is that a Hopf transform preserves this property, that there exists a two form in the neighborhood of E, which has simple pole along E. That means that the pair YF is also a Calabi-Yau surface. In particular, it can be a K3 surface. Great. There's a classical theorem by Castanova that says if you have a surface which is simply connected and whose canonical bundle is anti-effective, then this is a rational surface. 2.0 plus dy anti-effective implies rational. Cool, we're almost done. If you know that the minimal model of the surface is B2, then it must be a blow-up in 9 points, because otherwise it's not going to have an elliptic curve of degree 0, or square 0. Theoretically, it can have a minimal model which is a Hirsebruch surface. But actually, it can't. And I have -3 minutes to explain this. I guess I'm not going to explain it. You'll just have to believe me that the minimal model has to be and I'll finish here.
Questions?
Maybe. So this surface that you consider, so if I remember correctly, you take this elliptic curve, and there are like some maps that contract this elliptic curve to an elliptic singularity, and these are singular surfaces which move things to K3.
You can contract this elliptic curve because it has square 0.
No, you have to blow up something more.
Well, let's do.
You have to. There's some trick that you blow up like 1 point more. I forget how it is exactly, and then you manage to contract. And these are. I forget the name of these surfaces, but they're smooth things to K3s. So I was wondering whether one can compare the algebraic structures that you have on the K3 side and on this side.
Listen, I haven't thought about it.
I forget the name of these surfaces, but okay, I can check it.
Okay.
But then you modify also the complement of the curve, because...
Yeah, you also add some part of the rational curve.
Yeah, I forget exactly how.
It's unclear how to remove.
You're right, you can keep on blowing up, and then the curve will have negative self-intersection, and then it's Grauers that's telling you that you can...
Yeah, but there's like kind of a specific construction that you blow up a 10th point kind of in a canonical way, and you manage to contract the elliptic curve, and these are kind of well-known surfaces which have a lot of relationship with K3s. So I don't know, it would be interesting, like there's like any relationship from the algebraic structures on the one side, because then you're removing the elliptic curve, so you just take the smooth part when you contract it. So
and how do you choose a 10th point in a canonical?
I forget. I'm forgetting.
It's interesting.
I have to look at that, but I can tell you like with the paper.
Still, the smooth locus of the contracted one is not the same as the complement of this elliptic curve. There is a copy of C that you add from the rational curve that you blow up in addition.
Yeah.
Further questions? Great, let's thank everyone once again.